So our speaker for today is Giovanni Bocchi, which will talk about hitting the ends, computational approaches to the harmonic measure of a square. Please, Giovanni.
Thank you, Federico. So good afternoon, everybody. As you said, I will talk about this problem, which is related with the problem of computing the harmonic measure, not really of a square, but of a rectangle. So I will first give you an introduction of the problem, and then we will see a bunch of methods for solving this problem in the possibly most numerical accurate way. And then some conclusion, essentially one reference. So first of all, let's introduce the problem. The problem is this. We have a particle at the center of a 10 times 1 rectangle that undergoes a Brownian motion till it hits the boundary of the rectangle. What is the probability that it is at one of the ends rather than one of the sides? The ends are the two small edges, while the sides are the two long edges. So first of all, I would ask you, does somebody wants to guess what is this probability? Nobody wants to guess? Maybe just the order of magnitude, I don't know, 0. Okay, it's small, but not really 0. Okay, so we don't have any hints from the public, sadly. Indeed, we have that p is of the order of 10 to the minus 7. And so our aim today will be to try to calculate p to 10 significant digits. So to an accuracy of 10 to the minus 17. It's really a hard task. And we will see some techniques, some successful, some not, to solve this problem. And so we will denote the objects essentially. So we will denote the rectangle as the product of those two intervals, the ends and the sides correspondingly as subsets of the boundary. So with this notation, we will see, as I said, a bunch of techniques. First of all, we start from the probabilistic interpretation as I defined the problem, so speaking of Brownian motion, and we will see a Monte Carlo approach. Then we will switch to the PDE approach with two possible approaches, one more numerical based on finite differences and one more analytical based on the separation of variables. Finally, I will give you the idea of using conformal mappings to solve this problem. And in the reference, there are also two more methods to solve the problem based on elliptic functions and singular moduli, which I will not introduce in this talk, but if some of you is interested, I will give you the reference. So let's see the first approach, which is a Monte Carlo approach. With the term Monte Carlo, we refer to a class of methods that try to approximate a certain quantity by finding a suitable, and with suitable I mean easy to sample from, random variable x, such as the expectation of x equals q. And then we can obtain estimates of the expected value of x by generating an IID sample x1, xn, so by generating independent and identically distributed copies of x, and by computing the sample mean. So essentially the mean of our variables. We are very happy because usually this estimator has very good properties. It converges almost surely. It is unbiased, so it means that on average this estimator really gets the true value of the parameter of the quantity q in this case. So in principle, it's a good approach to solve such kind of many problems actually. Let's see what we can do in our case. In our case, it's pretty clear what x should look like. We take a Brownian motion that starts from the origin of the rectangle we let it evolve till it's the boundary, so tau of the boundary of R is the hitting time of the Brownian motion, so the first time where the Brownian motion belongs to the boundary, and then we will see if the Brownian motion exits in the ends rather than in the sides. So that indicator function will be 1 if the Brownian motion belongs to the edges and 0 otherwise. So by the properties of the expectation, we get that the expectation of x is simply the probability that the Brownian motion exits in the edges, in the ends. And we have already seen in the previous talks that this quantity is exactly the harmonic measure of the rectangle with starting point at the origin of the ends. And so this is the connection with the previous talks that will allow us also to use the further techniques. So in principle, we could generate n full trajectories of W, so by considering a discretization of time and using something like Eulero-Maruyama methods, and we should count in the end how many of these trajectories it's the boundary in the ends. But actually there is a smarter way to do this using an algorithm that is called Wacom spheres. Here you have a sketch of the algorithm. This algorithm uses the fact that actually the Brownian motion is isotropic. So if you consider a sphere centered at the starting point of the Brownian motion, the probability of the Brownian motion going to every point of the sphere is the same, so we have a uniform distribution. And so simply we can consider at every step the starting point of the Brownian motion, the maximal, in this case, circumference that is contained in our domain, pick a point at random on that circumference, and then iterate until we are close enough to the boundary. If our point in the end will be closer than epsilon to the boundary, we will say that we converged in some sense, and we will count that point 1 if it is in the ends and 0 otherwise. We sum the values that we obtain and we divide by the number of samples that we generated in order to obtain an estimate for P. So here it's a little bit small, but you have 2 iterates of the algorithm. In the first one, the blue one, the first guess is already too close to the boundary that is considered as hitting the sides, and in the other, that is in orange, we do some iterates, but in the end we also get to the sides. And here you have a little analysis of this algorithm. We consider 2 values for the number of trajectories, 10 to the 7th and to the 8th, and 2 tolerances for assigning the last value to the boundary, 10 to the -2 and 10 to the -4. And we see that with, manageable times, we get those estimates for P that are clearly not very sharp, because in one case we get just 1 digit, and in the other we get just 2 digits, so probably just the first one is correct. And then we can say something why this happens. So we have a way to measure essentially the error of a Monte Carlo approach. We could try simply to compute the mean squared error of our prediction that by definition is essentially the variance of our estimator for P, that being P obtained as a sample mean reverts just to the variance of our random variable x divided by n. But since from what I said before, x could be modeled with a simple Bernoulli random variable of parameter p, we have that the variance is p times 1 minus p, but since p is really small, we get that this is approximately p, and so we can use also this fact that the expectation squared is less than the expectation of the square to conclude that our absolute value, our absolute error actually in expectation will be less than the square root of p over n. And we can use this information to argue that since p, we have at least the order of magnitude that is 10 to the minus 7, in order to bound this quantity by 10 to the minus 17, so to have almost 10 significant digits, we need to ask by reverting the inequality that n is larger than 10 to the 28, which is actually something unfeasible for every modern calculator. So, Monte Carlo approach, quite simple, very easy also to code, fast, but not very accurate. We can't even get 3 significant digits. So there is no hope that we will compute p to 10 significant digits. So we need to change our point of view and use the PDE approach, like the previous speaker did in the last talk on this topic. And so we have seen that the harmonic measure of a domain is strictly related to the solution of the following boundary problem for the Laplace equation. So we have that the Laplacian should be 0 in the interior of R, and we should prescribe the values of the boundary in order to have u equal 1 in the ends and u equal 0 in the sides. And in the end, we obtain P by evaluating the solution at the origin, at the point 0, 0, which is, again, by definition, the harmonic measure of the rectangle evaluated in the ends with starting point, the origin. So essentially, now we can try to obtain an approximation of P by solving numerically or in another way this PDE, this boundary problem. And as I said, we will see 2 approaches, the first one numerical, and the second one based on the separation of variables. So the first one is numerical, so we will discretize the problem using a finite difference approach. So on a grid RH, which discretizes the rectangle R, and which is made of 2 and x minus 1 points in the x direction and 2 and y minus 1 points in the y direction. And we will obtain essentially the discretized version of our rectangle, intersecating the rectangle with essentially a lattice of that kind, having the steps in the 2 directions given by the ratios between the dimension of the rectangles and how many points we took for the discretization. We would like to have a uniform grid, so with similar steps in both the direction, because usually are better. And so essentially we will choose an x as an integer multiple of n, and yeah, there is a typo that should be n dot y as another integer multiple of n. In order to approximate the aspect ratio of the rectangle, so the ratio between a and b, with those two numbers, R and S. Obviously, they are integers, so if the aspect ratio is quite irrational, that would be hard, but in our case, we have 10, so it's pretty easy to do that with integer numbers. So in the end, we define h as 1 over n, which is our overall discretization parameter, and we will discretize in the same way the boundary, saying that the discrete boundary is the intersection between the boundary and our lattice. That also decomposes into two parts, so the discrete ends, the points in the discrete boundary where x is equal to plus or minus a, and the discrete sides as the complement. So we have everything now. We need to solve the problem numerically because we will discretize also the equation using this kind of, which is called 5-point discretization. We use the discretization of the derivative with 5 centered differences both in the x and in the y direction, and so we obtain this discretization, this equation that involves essentially the values of the solution in one point and the values of the solution in 1 point up, down, the one on the left and the one on the right. So we have this kind of cross shape that moves in the mesh, and that gives us the approximation. So we have that this quantity, to respect the equation, should be 0. And so we have that UH will be our discrete solution defined on the intersection of our on the union of our discretization grid and our discrete boundary, with the two properties that on the ends, on the discrete ends, it equals 1, and on the discrete sides, it equals 0. So this essentially has to do with the boundary conditions, because when we put into the equation a value of I and j for which one of those numbers belongs to the boundary, we will have that the value of u is prescribed, so it will no more be unknown, and it will pass to the right-hand signs, constituting essentially a right-hand sign for the equation. So for this, I mean, after eliminating the boundary points, we can essentially unravel the solution into a big vector. This is xn. So essentially, here UH is expressed essentially as a matrix with two indexes. Here xh is UH unraveled, so where we take all the rows and we stack them to a column, a single column. And in the same way, we will construct this matrix AH, which is of dimension began times began, which is the product of these two terms, which will be essentially a positive definite matrix made by just 5 non-zero diagonals. So it's essentially everywhere 0, but 5 diagonals, which is strictly related with this fact that we have 5 points here. And so essentially we turn this equation into a linear system where where the term BH, the known term, is essentially what we obtain from the boundary condition. So we don't have 0 as we have in the equation, because there are the contributions of the boundary terms. Yes.
Maybe I missed something. The 5-point discretization is a standard technique, or so the reason of why 5 points is that the standard
5 points
is
is since you discretize the second derivative with the center, the second difference. So you get 3 terms. One is centered in the point where you are, and then you obtain the one on the left and the right, or top or bottom, considering the direction in which you are. And then by summing them, you just get those. So you have at the end 5 points.
5 points are like this one.
4 points are like.
Oh, okay.
Maybe that. Five points because of this. Here you have ij, here I minus 1j, I plus 1j, here I j plus 1, and I j minus 1.
Okay.
And so to obtain the approximation, here essentially you involve just those 5 points. Yeah.
Why they find the differences are not different?
No, you can do also finite elements, but finite differences are easier, I mean. So, no, you can do whatever you want for the discretization of a PDE here. Okay, so we define that linear system. In the end, we just need to solve that linear system. There are a bunch of ways to solve that linear system. In particular, we can exploit the fact that AH is positive definite, so it's something that can be useful. For example, here there is a very simple code in MATLAB to obtain the solution. So I don't want to go too much into the details, but the matrix A is really obtained by the Kronecker product essentially of these 2 small matrices, which are essentially the matrices with 2 on the main diagonal and -1 on the first down diagonal and the first upper diagonal. So by making this little combination of the 2, we really obtain the matrix A that we need for the problem. Then we simply solve in a really lazy way the linear system with the / command of MATLAB, and so we obtain our solution. We will then have the uval, so essentially our estimate for P, as evaluating U at the point of the discretization that is closer to 0, 0, 0. Actually, here we chose a discretization in which we always have 0, 0 as one of the points, but in principle it could also do not belong to the grid, to the discretization. So here there is a plot of the numerical solution. As you see, it's a function that really decays very rapidly, very fast to 0, respecting the constraint of being 1 on the ends. And here we have also, we need to pay a little bit of attention, because clearly these boundary values is not continuous on the boundary. So we usually know that the solution should be continuous up to the closure of the boundary. But indeed, we could request actually that is continuous up to the closure of the boundary minus a finite number of possible points of discontinuities. So in this case, we have that the corners are 4 points of discontinuities. So we are happy also from a theoretical point of view, we could solve this problem by finding something that is continuous but on the corners. Okay, so choosing H 1 over 128, that leads to those values for an x and y, we get that that function in MATLAB returns this value for P. So the order of magnitude and the first three were taken correctly. Here we don't know actually how many digits are actually correct. Now we can use some results from a priori estimates for the solution of for the numerical solution of a PDE. And so here we could bound the error in subnorm with a constant k infinity of h, which is the condition number of the matrix, which for this kind of matrices scales like big N. Epsilon h, which is the precision of the machine, so the numerical precision, and the norm, the infinite norm of the numerical solution. So by revising just a little bit this inequality, we get that the approximation above should be correct, but only to 4 significant digits. Indeed, it's correct just to 3 digits, so the 3, the 8, and the 3. Nonetheless, there is a common technique for finite differences, which is Richardson extrapolations, that usually uses the error to increase the accuracy of the numerical scheme, which is already an order 2 scheme, so it's already quite accurate. And with that approach, we could get a solution with 10 significant digits, actually 12. But I didn't report it for questions of time. So Monte Carlo approaches, we got just essentially 1 significant digit. Here we did something more. We got 3 significant digits, but still with the pure, finite difference approach with no machinery in addition, we couldn't get what we wanted. So now we try a second approach, which is based on an analytical approach, uses separation of variables. And so we look to a solution of our problem obtained by an infinite sum of the product of functions depending only on x and only on y. This is a classical technique for solving some kind of PDEs. We then apply the Laplace operator, and we obtain that for every k, the 2 functions v and w should follow this other equation. So in the end, we obtain that these 2 ratios, which depends, the first one only on x, the second one only on y, should be equal for every k, and so for every k they should be equal to a constant depending neither on x, neither on y, that restricting to the case of w leads to this boundary problem for w. Actually, it's an eigenvalue problem for w, where we have that we have this equation for w and the 2 boundary conditions, that w evaluated on minus b and b should be 0. So this is quite easy to solve, and we have that the exact solution is this cosine evaluated in this point, and the lambdas, the eigenvalues, are essentially these numbers here. Then, to find v, we should evaluate what we had before at x equal plus and minus a, so that the part in x becomes a constant, depending possibly on k, and we have that the evaluation of the function should give us 1 for every y in minus bb. Then from this equation, we use essentially that wk are eigenfunctions, and they form an orthogonal system. So taking the integrals and by multiplying by a wj, essentially, we get this equation that allows us to find ck for every k. So ck has this value, and then we can revert to the equation for decay, which is very similar, but we don't have the homogeneous condition. We have this CK here. Again, we can find the solution analytically, which now involves hyperbolic functions, the hyperbolic cosine, and has this shape where we have in front CK and this ratio of hyperbolic cosines. So in the end, the solution, we just need to sum everything and multiply as this form. If we evaluate it in the point 0, 0, we obtain this series where I changed A over B with rho, which is the aspect ratio of our rectangle. So actually this is quite an interesting series because it is an alternating with coefficients that monotonically goes to 0. So we can apply Leibniz criterion to say that it converges, but also we know that the limit is always enclosed within two successive evaluation of the partial sums. So now we will exploit that having this hyperbolic secant is made of exponentials, so very fastly decaying to 0, we could obtain an estimate of this value, but by just summing, the first one or two terms of the series. So in particular, we get that just already an approximation within the two first iterates. So just the first term and the first two terms of P of the series gives us an estimate for P that is actually correct up to at least 14 digits. So we see that they agree at least until the 14th digit. So we're happy. In this case, we obtained 10 and even 4 more significant correct digits. And so this is essentially the first approach that allowed us to really solve this problem, and that used this essentially the fact that we could express the solution evaluated in the point as a fastly decaying alternating series in order to get the final result. So something that could look like an analysis 3 probably result. Okay, so we can go on and see the last approach for today, which is based on conformal mappings. Okay, so we will define very naively a conformal map as a map from two open sets over n, which locally preserves angles. You have to think about that if you take two paths on U and you map them on V, which are incident in a point, the tangent vector to the paths on in that incident point should have the same angle as in U, should form the same angle as in U. And we have this theorem which is restricted only on R2. So we have, if we have omega, which is an open subset of the complex plane, then a function from omega to C is conformal if and only if it is holomorphic, so differentiable in the complex sense, and this derivative is everywhere non-zero on omega. Then we have this other famous result, which is the Riemann mapping theorem, that proves that if omega is non-empty, simply connected, open, and not the entire complex plane, then there is a biholomorphic mapping F, so bijective and holomorphic was inverse is also holomorphic, from omega onto the open disk. The open disk, so without the boundary. And so by this theorem, F is a conformal map from omega to D, and also the inverse is a conformal map from D to omega. The key fact of conformal mappings is that they also preserve the harmonic measure. So in our case, we should have only to construct a conformal map from the disk to our rectangle, which here I'm cheating a little bit because this rectangle is not A, B, but is 2A and 2B, and you will see in the following why. So in order to obtain these numbers without the fractions, essentially, but the aspect ratio of the rectangle 2A times 2B is always A over B. So the P should be the same. So, okay, we should try to find this map where A, B, C, and D are these numbers in the complex plane, where A and B are not the usual letters that we put for defining complex numbers, but are those of our problem. So there are a bunch of results that allows us to obtain this map. First of all, we have that by the Riemann mapping theorem, we have that map, but there is a reflection principle of Riemann and Schwarz that tells us that F is one-to-one and respect the symmetries with respect to minus and the conjugation. In particular, so we have that F of 0 is 0. And lastly, by this other result, by Osgood and Karateodori, we have that conformal map F extend as an homomorphism of the closure of D onto the closure of R, because the Riemann mapping theorem only ensures that we have the map from omega, which is open, to D, which is also open. But to speak about the images of the corners and the edges of the rectangle, we should have also something that is continuous up to the boundary. And so we have that the preimages of A, B, C, D should be A prime, B prime, C prime, and D prime, which are these complex numbers here, represented on the boundary of the unit disk, where we essentially have this angle phi between A prime and D prime, which is the same between, subtended by the arc from A prime to D prime and from B prime to C prime. And so we have that this angle in particular, we don't know it yet, but it's between 0 and pi. So the last result that we will use is that now we know what is the harmonic measure of an arc of a circumference, because in the past talks we saw that the harmonic measure of a circle is the uniform measure for that circle. So here we are considering the harmonic measure of the disk, of the border of the disk centered in the point Z equals to 0, with E prime essentially the union of those two arcs. But essentially we obtain that P, which is the same P as before, is the harmonic measure also in this case, and so we obtain it as the essentially relative length of the union of those arcs divided by the total length of the boundary of the circle. And so by simplifying, we obtain that phi is equal to pi. So we have what, if we know phi or p, we have the other one. Lastly, the last result that allows us to really obtain our estimate is the Schwarz-Christoffel formula that says that we can obtain the value of the conformal mapping as the value at 0 times a constant times this complex integral of this function, where we should take a product over the complex numbers of the preimages of the corners of 1 minus zeta over w, where the exponent is essentially 1/2 minus 1, because at every point, every corner of the rectangle, if we consider the exterior angle, we have pi over 2, and this is equal to alpha pi, where alpha is this factor 1/2 that appears at the exponent, and this is the same for all the external angles to the rectangle. So those exponents are the same for all the 4 terms of this product. So by substituting the values of A prime, B prime, C prime, and D prime, we obtain this expression. We can simplify it by considering the product of the first 2 terms and the second 2 terms, and then by substituting to phi, p times pi, as we obtained. We have that f of 0 is 0, as already pointed out, for reason of symmetry. Lastly, again, by the properties of symmetry, C needs to be a real constant, not complex. And now we try to evaluate the integral on a radial path from 0 to A prime. So this is our path, and we will make essentially the substitution that leads us to this now real integral with just complex numbers in the denominator, and we can take out this e to the ip pi over 2, and we are left with this integral that I will denote as k evaluated in e to the ip pi, where k, big K of little k, denotes the complete elliptic integral of the first kind of modulus k, which is defined here. So here we see that our k squared is e to the 2 ip pi, and so our k is e to the ip pi. So if we are essentially able to compute this integral, we could then obtain something for p. But to obtain an estimate of p is essentially not required actually to compute k analytically, because we can take the complex arguments of both sides, because we add that f of A prime, here I didn't wrote it, but was A, and A was exactly A plus EB. So if we compute it, its complex argument should be the arctangent of B over A, and so the arc cotangent of A over B, which is our aspect ratio here. Okay, the arc cotangent of the aspect ratio should be equal to the argument of this first term, which is exactly p pi over 2, as we have here, and then we sum the argument of that complete elliptic integral. Here we have a transcendental equation for both p and the aspect ratio, essentially, and we could use another software, which is Maple, to solve this equation, or also Mathematica. We simply code the equation, we request a precision of 16 digits, and we obtain the estimate for p by solving this equation, this time really at 16 significant digits. So again, we solved the problem using the tools of complex analysis this time. So concluding, we solved the problems in many ways, some simpler, some harder, some more precise, some less precise, and it should be also interesting to ask about the generalizations of this problem. In particular, what if the particle starts at some point that is not the center? If we have a general polygon and not a rectangle, but still in 2 dimensions. Otherwise, if we go in n dimension, but we stick to the box, and so we have an n-dimensional box. So we saw the first 4 methods where we have this level of precisions. Essentially, Monte Carlo is the simpler and works for every of these scenarios, and essentially is usually a very good approach, in particular in higher dimensions. Finite differences work for the off-center and the n-dimensional box, but are a little bit more tricky for a general polygon in R2, while separation of variables really works only for rectangular domains and not for polygons, and conformal mappings really work for off-center, every polygon in 2D, but they have no direct generalization in n dimension. And the other 2 approaches that we didn't see, which both leads to high precision, in particular with singular moduli that are particular solution of these elliptic integrals of the first type, we could get a closed form solution for P, so obtained by the product of some radicals. But this is the less generalizable approach because it's essentially rooted to having a 2-dimensional square domain and considering the center. So computing quantities similar to P are interesting problems for many kinds of applications, and so one could argue which is the best method regarding the context. So this ends this presentation, and I essentially used just this reference, where if you are interested, you can find another bunch of references for essentially all the methods that I presented. So thank you, and if you have questions, you're welcome.
Okay, thank you, Giovanni. Is there any question?
Yes.
Okay, so maybe I misunderstood what you said in the beginning, but when you started your PDE approach with the Laplace equation and everything, I was wondering, okay, you're basically considering this in a rectangle, so you have different measures of the sides and on the endings. I was trying to figure out what happens if I just shrink the rectangle into a square, perfect square. Does it simplify in a sensible way, or you have problems with this approach and you have to modify it a priori?
No, it's simpler. Actually, finite differences actually works even better with a square domain. So no, there are no problems. And in particular, in the case of a square, it's quite easy because the value of P is 1/2. So
sorry, no, I was asking about the system, the PDE system, the PDE problem here.
okay.
Because I was wondering, well, if I get the point, you have the Brownian motion starting at the center of your rectangle,
Yes.
and then you have to reach the ends. But
Yeah.
if I have all the sides of the rectangle that are equal, you get more symmetry. And I was wondering, how can you distinguish in that sense between ends, and sides?
No, you can't exactly. So if you have essentially the square, which is the most symmetrical case, you could choose a couple of opposite edges to be the ends and the other one to be the sides, and the choice is equivalent, and you get in both cases p equal 1/2.
Okay, so you put your function to be equal to 1.
Yeah, for example, here and here, and you get 1/2, but it's the same if you make the opposite choice. As you start to stretch the square into a rectangle, you get different results. If you, I think that there is another example in the book where you consider again a rectangle where the aspect ratio, if I don't remember wrong, is square root of 3. And in this case, if you always set 1 on the smaller edges, you get that p is 1/6. So it goes to 0 as you the most you shrink the rectangle. But essentially all the methods apply for every kind of shrinkage that you choose.
Is there any other question? If not, well, let's thank Giovanni again. And we're meeting tomorrow.